In this class, we're going to take a look at how you solve trig equations which contain a double angle. So a double angle being like sine 2x instead of sine x, or cos 2x instead of cos x. So although these are a little more complicated than if you don't have a double angle, like a single angle, it's still going to use the same sort of techniques as we would for any trig equation. So cast diagram, considering radians, considering the range of values that you're allowed for your solutions, considering how to use the inverse on the calculator or how to use exact values if it's a non-calculator question. All of these usual trig considerations come into play with these as well, just with like an added layer of complexity. There's a few different question types in this topic, but generally what we're going to do is use the double angle formulas. So if you're not familiar with the double angle formulas, either follow along and then check them out later, or maybe check them out now and then come back to this class. But basically the double angle formulas allow you to take a double angle like sine 2x or cos 2x and turn it into a different expression which has got a single angle. So we're converting using a double angle formula to make it into a single angle. One thing about the setup of these, you cannot really solve this equation or this equation as they are, because when you're solving for x, but these equations have got both x and 2x as the angles. So you've got to either solve for one or the other. You can't solve for both like at the same time. So that's why we effectively just take an approach where we get rid of these and change them using the double angle identities into something else. Okay, so I think we might actually start with this one. So there's a sine double angle formula. There's only one sine double angle formula. That's why this one's a little easier. So the double angle formula for sine says that sine 2x is equal to 2 sine x cos x. So what we're going to do is just take that identity. I'll just kind of put that in a bracket to keep it as like side working. We're just going to take that identity and plug it in there, okay? So we're just saying that the sine 2x now becomes 2 sine x cos x. Keeping the rest of the equation, so plus cos x equals 0. How we proceed from this point depends on what expression you've got here. It depends what the equation looks like. This one's going to probably look a bit different at this point. What we're generally going to do though is to factorize, and how you factorize will depend on whether it's a quadratic expression, which I think this one will be, or a common factor type expression like this one. Common factor in the sense that we can factorize it using a common factor. The common factor is cos x. So if you're not used to using trig functions as a common factor, it might seem a little bit weird at first because often we factorize using numbers or simple algebraic terms, but there's nothing to stop you using a cos x. It's still a common factor between these two terms. So I'll factorize with my cos x. That will give me 2 sine x plus 1 inside the bracket equal to 0. And then we're just going to take these guys and split them off into two equations. So for this guy, we get cos x equals 0, and this guy we get 2 sine x plus 1 equals to 0. Then basically we've just got to go ahead and solve these equations. How you solve those equations will depend on whether it's a calculator or non-calculator question. It will depend whether you're in degrees or radians. Let's say that this question is in radians, so we're going to work in radians between 0 and pi. So that's a bit of a restriction on the range of values, only going to pi. That might restrict the number of solutions. This one here is one of the extreme values, I would say, for cosine. So what we're going to do for that one is consider the cosine graph. Cosine graph goes like this. We've got cos x equals 0. We're only going out to pi, so pi on the cosine graph, that's 180 degrees, is this kind of middle point here. Well, it would be in the middle if I hit the middle. That's meant to be down the middle, something more like that. So we're not allowed to go beyond that point, basically. So the only point where cosine is 0 is there. That's pi by 2, 90 degrees. So that tells us the only solution to this equation is x equals pi by 2. Okay, so turning to the other one, it'll require a little more algebra. So we're going to start by rearranging. So sine x equals minus 1 over 2. I'm not going to focus too much on how you solve this. If you're not sure of the details, maybe check out a class on just solving basic trig equations first. But basically we would make a reference angle, which we get by doing inverse sine of 1/2, which comes out to be 30 degrees, which is pi by 6. We're going to need a cast diagram just to check our quadrants. We've got sine equal to negative. So we're going to check these two. So that's here and here. Problem here is that these two checks are beyond 180 degrees, so beyond pi, if we're doing the cast diagram in radians. That means that although we could get solutions to satisfy this equation in these quadrants, our range of values is such that it stops here at pi. So we're not allowed to include those solutions. So even though the pi by 6 reference angle, we would then use that by adding it to 180, adding it to pi, that is, in radians, subtracting it from 2 pi to get these two solutions. They would satisfy the equation, but they're outside the range of values. So they are solutions, we're just not allowed to include them. So that means that for this very elaborate, looking equation, it doesn't look like an easy equation. There is only this one very simple solution. That's mainly though because we've restricted the range of values. Okay, so that gives you an idea about how we use the double angle formulas in these equations. That is really the key, is using the double angle formulas to solve these, to make them into an equation that is solvable. So taking a look at this guy, this one's a little more difficult because with sine 2x, you've only got one choice. It has to be this double angle formula. For cosine 2x, if you're familiar with the double angle formulas, you'll know there are three choices. How you decide depends on the rest of the equation. Basically what you do is you want to match up the version of the cosine double angle formula which matches up with this. So there's one of the versions which only has a cosine in it, so that's the one you want to go for in this case. So we're going to use the double angle formula which says that cos 2x is 2 cos squared x minus 1. So notice the introduction there of a squared term, which means that we're going to be turning this into a quadratic equation. So a quadratic trig equation. It's pretty ugly, right? But just kind of like a normal quadratic equation, sort of. So plugging this into here, we're going to replace our cos 2x with 2 cos squared x minus 1, leaving the rest the same. So plus 3 cos x plus 2 equals 0. I'm going to combine our two number terms and write it as a trinomial. It's a trinomial in cos x, so not a trinomial in normal x. That can be a little confusing if you've never seen those before, but it's just like a quadratic equation, which hopefully you're familiar with, where this is your x squared term, your x term, and your number term. It's just not an x term, it's a cos x term, but it's kind of the same structure. This is a trinomial which we can factorize into two brackets. Sometimes this can be quite difficult with trig terms, but it works in the same way. To make a 1, we would need a 1 and a 1. To make a 2 cos squared x, we would need a 2 cos x and a cos x. Looks a little unusual this if you've never seen this kind of factorizing before. In this case, a plus and a plus would do it, so that's not too bad with the factorizing. What we then do is kind of like what we did over here. We just split it off into two equations. So this guy is going to give us 2 cos x plus 1 equals 0. This guy will give us cos x plus 1 equals 0. So they came out fairly similarly actually. So this one here, we can rearrange to cos x equals minus 1. That's one of the extreme values for cosine, so probably best to solve that by thinking about the graph. In fact, let's just go back and, because I forgot to define the range of values, let's say we're working in degrees this time, and let's say we're running all the way out to 360 degrees. So the cosine graph going to 360 degrees is like that. We're trying to think, where does it hit minus 1? Well, minus 1 is this point, lowest point here. It hits minus 1 at 180 degrees, which is pi radians, or 180 degrees if we're working in degrees. We're in degrees this time, so we can say the solution to that equation is x equals 180 degrees. So turning our attention to this guy, we get cos x equals minus 1/2 after we rearrange. For this one, we're going to need to consider a cast diagram. I might just get rid of this to make a little space. We didn't really need a cast diagram for this one because the cast diagram is just another way of visualizing the graph. So we use the graph instead. So this one probably does need a cast diagram. So CAST. We've got cosine equal to a negative value. So that's going to be a check here and here. This is 90 degrees. This is 180. This is 270. So we want solutions between 90 and 180, between 180 and 270. What we need to think about is the inverse cosine of 1/2, so dropping the negative. The inverse cos of 1/2 from exact values comes out to be 60 degrees. Again, if you're not sure about how I'm getting this or how I'm working with this cast diagram, maybe check out classes on those kind of topics first and then come back in here, because it is quite a lot of technique that I'm kind of pulling together. So this would be a reference angle because it's not one of our solutions because 60 degrees is in here in the first quadrant. So we're going to get our solutions by doing 180 minus 60 degrees and 180 plus. So that says that x is 180 minus 60 degrees, which is 120 degrees. And the second solution there given by 180 plus to get us into the third quadrant, which is 240 degrees. And we're done. So for this one, we've got three solutions. X equals 180 degrees, X equals 120 degrees, and X equals 240 degrees. So these are very typical examples of trig equations with double angles. The key really is to know your double angle formulas, try and memorize those, or they may be presented on like a formula sheet. And then knowing about how to use them, and particularly how to factorize. Once you factorize and split off into your two mini equations, those equations are really just standard trig equations. Of course, you need still to be comfortable with solving standard trig equations, so that's really maybe where to focus. I mean, getting to this point is kind of an algebraic exercise. Most of the work really in these questions tends to come at the end. This is where most of the skill is. You've got to think about cast diagrams and exact values and graphs and all that stuff. So there's a lot to pull together here. It is quite technical. Just make sure you've got the fundamentals first, and then when you're ready for this topic, definitely try some practice questions.